Good morning. La 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 la. Good, so let us start. Welcome. Today we will explain the last part of the homework. I shall apologize that I again posted the Zoom link by mistake just at the last minutes. But well, I see that many of you are here. Right, I didn't look yet at the submissions. I hope that all of you could submit your homework. It should be all okay. And well, I understand that's busy time for you now. There are many courses to take care of. But however, we will have also pre-exam today at 3 o'clock. As you remember, I just wonder, could you please type into chat if you are going to take part in this pre-exam today, just to understand how many of you we shall expect. So if you are going to take part in pre-exam today, please let me know in the chat now. Good. Thank you. I see that almost everybody is going to do this. Very good. So about 3 o'clock, as there will be automatic sending, hopefully it will work, automatic sending of the exam papers to you. Right, so I guess we can start. Kas, Hristo, who is the first?
I'm the first. I'm doing homework 9.
Kas, I guess you are muted. I can hear you at least.
Okay.
Yeah, you're fine, Kars.
Okay.
Right. That's good. Then let us see. Let me check if I started recording. Yes, recording is going on. Then I will switch to course. Just a moment.
Yes. Yeah.
Right, the floor is yours now.
Okay. Can you enable sharing? Julie, can you enable sharing?
Oh, I'm sorry. Yes.
Yes. All right. All right. I suppose everybody can see this. So, yeah. Okay, so I'm going to discuss homework 9, in which we're given this Hamiltonian here. We have some matter part with this omega here. This is bigger than 0. You have two boson modes. You have also a boson bath and an interaction. Yeah, I use this convention here. So the x hat is given by this thing here. You have R that's defined like here. And in the electric field, you have this coefficient which I call nk, and I write it like this. Yeah, that's then my convention. Okay, so in the first part, we're in question A, we're asked to calculate the final states and give their energy. So we prepare the system in this initial state here, the first excited state, which, yeah, you just excite one mode from the ground state. And the ground state is given by this thing here. So because it's positive frequency, the ground state is just a vacuum state, because that has the lowest energy. This state has, or the first excited state has this energy, h bar omega 0. And if you let the interaction Hamiltonian work on I, you'll find you can find these states here, and they all have energy 2 h bar omega 0 plus h bar omega k. You can also have a vacuum state here for the boson bath, and you can also have this state, which is again just the vacuum state, and then one photon in the boson bath, and it has energy h bar omega k. Okay, so but due to the delta function, due to the delta function in Fermi's golden rule, only this state is allowed. So due to energy conservation, because the argument of the delta function here can be positive or negative, whereas here it's always positive for these states. It's always positive, and therefore the delta function can never be, it will always be 0. So due to energy conservation, only this one is a final state that is allowed. Good. Then we're asked to calculate the matrix element given this final state. So, okay, you just take the expectation value of the interaction Hamiltonian. You plug in the initial and final state we found, and here I wrote down the parts which contribute, and then in the end you'll find that it's the matrix elements are given by this thing here. And then the decay width, just take the absolute value squared and of this matrix element. So you get, well, what's written down here. You have a squared e to the x alphas plus b squared e to the y alpha squared, and then times this delta function here. So that's the second part of the question in A. All right. Good. Then in B, we need to calculate the emission intensity for the different polarization directions. So first you convert the sum to an integral, and then I integrate over k to get rid of the delta function. And then I'm left with this expression here. And if I use the polarization factors, which are given in the question, these here, I plug them in, then you'll find this result here. And yeah, so, okay, that's first part of B. Oh no, that was B. Okay. Then in question C, we're asked to calculate where this emission intensity is 0 for different polarization directions. So let's look at the polarization direction 1 and see when that is 0. So well, that means that this thing here must be 0. So we can take out this cosine theta squared. I can set it to 0, and then I see that theta can be pi divided by 2, and a, b, and phi are free to choose. And on the other hand, we can have that this thing here is 0. So if I solve for cosine phi squared and use the relation that a squared plus b squared is equal to 1, this normalization condition of the first excited state, then we find this relation here. And yeah, theta is free to pick. And yeah, if I write down possible solutions, so you have a, b, theta, phi, then in the first case that reduces to a and b and phi are free to pick, and theta is equal to pi divided by 2. And for example, you can pick a equal to plus or minus 1. And then from that follows that b is 0. And well, theta is free to pick, so just leaves theta. And because of this relation here, we derived phi must be equal to pi. There are more solutions, but I just chose to write down this one as an example. Okay, and then for point 2 in the question, when the polarization direction of 2 doesn't give anything, so the emission intensity in that direction is 0, then we need to solve this equation. But similar to 1, only now you have 1 minus b squared instead of just b squared. And in this case, theta is free to pick, so I wrote down again some solutions here. So you can have a is 1, a is 1 plus or minus 1, then b is 0, theta is just 3, and phi is pi. So yeah, and there are more possible solutions just written down here. Okay. So then point 3, when is the total emission intensity 0? Well, then you want to have case 1 and case 2. So we can set the first emission intensity to 0 by setting theta is equal to pi divided by 2. Then we ensure that gamma 1 is 0. And yeah, a, b, and phi are free to pick. And yeah, I can just use solutions from point 2 and plug in theta is equal to pi divided by 2. So if I do that and we have these combinations of a, b, theta, and phi, which will give a total emission intensity, which is 0. Okay, so that was 9C. Oh no, almost. We also are asked to calculate the whole decay width. All right, so yeah, just using these relations for the integrals. So the integral over phi will give this pi here. And I used again that a squared plus b squared is equal to 1. And yeah, you can use that this integral is equal to 2 and this is equal to 2/3. If you plug that into gamma 1 and gamma 2, then you just find this. And if you add these, then then here is written down the answer. You can maybe simplify this further to this form. So you have 4 alpha omega 0 to the power of 3 divided by 3c squared times r squared. Okay. Yes, in 9D, we're asked to calculate the Heisenberg equations of motion for all the caps in the Hamiltonian. So we can use this relation here, where the time derivative of this operator is given by the commutator of A with H. And well, if you do it for example, bx, then well, you get the commutator of the whole Hamiltonian, which is written down here with bx. Oh yeah, and we added the force to the Hamiltonian here, only in the x direction. Well, the only parts that are giving anything interesting is the part where, yeah, the commutator of bx with the matter Hamiltonian and with the interaction Hamiltonian here. Yeah, the phonon Hamiltonian just contains caps of the photons, so the commutator of bx with that is 0. All right, so if you do these commutations or write down the work out the commutation relation, then you obtain this relation here. Right, and if you do the same for the by cap, then well, you do basically the same steps, only you don't have this force. This force doesn't appear in the by equation of motion. And oh yeah, then we also have the cap of the photon field, so of the photon, and yeah, the only part that gives anything is when you look at the commutator of AK with the boson bath and the AK with the interaction part. And if you write it out, then you find that this is the answer. And then for the creation operators, well, you can just take the Hermitian conjugate of all these here, and that's how you obtain the equations of motion for the creation operators. It's basically the same steps. You can also do the commutation relations, but here I've written down the result here, so you can maybe look at it and check it. But let me continue. Yeah, and in 9E, we're asked to do the Fourier method to solve these equations, and we're asked to calculate this G. Okay, so first about the Fourier method. So you decompose this time-dependent operator here, bx of t. You replace it by its Fourier modes, bx, and then if there's e to the I omega, you just do a Fourier transformation. And basically what changes, if you take a time derivative here of this operator, then you get I omega down. And yeah, so you can do these transformations to the equation of motion we just saw. And if you do that and don't write down, I choose to not write down the integral and this I omega t because it's annoying to carry that around. Then you obtain these equations of motion here. And what we want to do is we want to solve these bx's, bx and bx dagger. So in order to do that, we want to know what the solution for ex omega is. So first what we need to do is look at this ex omega. Well, this ex omega consists of the creation and annihilation operators of the photons. So we need to look at the equation of motion for that. If we do the Fourier transformation, then we obtain this here. And if we solve for A, then, well, you take this to the other side, and then you divide by h bar plus h bar omega k, and you will obtain this relation here. And if you do the same for the creation operator, then you'll obtain this equation here. And it's stated in the question that we can disregard expectation values in the y direction. So that's why I skip this part, this part which is proportional to y hat, because in the end it will not contribute. So when I plug it back into ex omega, I only take the x part here. And yeah, so if you plug in these creation and annihilation operators back into EX, then you find this relation here for EX. Okay, so now we can plug that back into yeah, the equation of motion we derived. Yeah, well, oh yeah, so you can solve that in terms of Bx, and then you add Bx and Bx dagger, multiply by R, and after some algebra, you'll obtain this equation here. And if you want to, you can again solve this. You can rewrite it a bit into this form here, and take the expectation value, and you'll find that this G omega is the thing which is defined here. So yeah, it's a lot of algebra, the last one, but this is how you do it. And that was homework 9. So if you have any questions, I'll be happy to answer them. Are there any questions?
Right, are there any questions? I don't see. Okay, there is a question.
Nope. Okay. Okay, then I stop the share.
There is a statement about the absence of questions. Sorry.
Oh.
Good. So I hope that everybody has solved it. I've several students who contacted me yesterday. There were some misunderstandings. Mostly recon about computation of this matrix element, which was a bit unusual because we seldom do it for a superposition of two states. Right, so there were some small misunderstandings with this. So I hope you all did it all right. So thank you, Cars. I will see if Hristo is available. Right, it looks like this. Yes, well, I will give you spot light.
Okay. Okay. Can everyone see the screen that I'm sharing? I guess if you don't protest, then everyone can see it.
I can see that.
Let me just open. Okay, so this is going to be the last homework problem for this year, homework problem number 10. And we're going to talk about master equation for lasers. So this problem has been discussed also in the book in a more simplistic way. Let's see how it goes. We first consider a simple model of laser that is also presented in the book. We have atoms that are pumped to the excited state with the rate R and decay naturally to the ground state with the rate gamma, big gamma. In addition, the atoms can decay into the optical modes. So in distinction from the simple model that in the book there is only one such mode, here we have infinitely many such modes. And they're labeled with the integer m. And for each atom, the emission rate is given by, let me use some color. So it's given by the following formula. Gamma m is gamma 1 plus m squared kappa squared, where kappa is assumed to be very small. All those modes will have a frequency that's the same, omega, and they have the same quality factor q. And we denote the total number of excited atoms by capital N excited. So in the first question, you're asked to derive or just write down an equation that's similar to the one in the book, but instead of a single mode, now we have to consider m such modes. So let us. The equation is quite simple. We just need to replace everywhere n by nm, the following index for several modes, and gamma with gamma m. And we have the following equation here. Now the next task is to express the stationary number of modes in terms of the number of excited atoms and the decay rate of each mode. For this, we just put one side of the equation. So we put this side of the equation equal to 0, and we find the stationary solution to this equation. Again, expressed as the decay rate, the number of excited atoms, and a ratio between the frequency with respect to the quality factor. So in this model also, by definition, the number operator can take only values that are either 0 or bigger than 0. And from this definition that we have, we can express from this following equation, we can express an equation for the number of maximum excited atoms that I write here. So we just simply take this equation, put it bigger or equal to 0, and the number of excited atoms is maximum if we have an equality, such that the number of modes is 0. Makes physically, it makes a lot of sense, means that all the atoms are excited and there are no modes that exist, no optical modes that exist. Okay, I'll move to question B now. It's merely a question. You're just asked to derive an equation for, there is an error here, so yeah, there is no t here. Maybe in the text we need to correct it in the text also. So just for the derivative of the number of excited atoms that is similar to the equation of the book. And again, the only thing that needs to be considered is that this time gamma depends on m and n depends on m, and we need to sum over all possible modes here over this. So that's what you're asked to find. Let me see. I cannot see if there are any questions in the chat. I don't think so. Okay, no questions. Now, yes, let me just have the chat. Then we can move to question C. So in question C, it's just a little bit of algebra or denoting different quantities and trying to obtain dimensionless equation for the stationary number of excited atoms. So in question C, what you're asked to do is to substitute the stationary solution that we have found in question A, point A, to this solution in point B. And by introducing rescaled quantities, so R, which is just R divided by the number of excited atoms times the decay rate, and A, which will be the ratio between the number of excited atoms with respect to the number of the maximum excited atoms. So this quantity can never be bigger than 1. It goes from 0 to 1. And then they give you a specific form for the equation that we want to obtain with the defined quantities. This is the equation that we have, where x of m depends only on a and kappa, and you're asked to just to find what are the x of m. So here I do not perform all the algebra that is needed, but one can see quite easily. Let us look at this equation in question B. Maybe yellow is not so important. Let me use blue. We look at this equation. So this term will be equal to 0 for the stationary solution. Then what we need to do is to take the whole equation and divide, for example, to obtain the quantity R. We see that we have an R here. We just need to divide by the number of number of excited atoms, the maximum number of excited atoms, times just gamma. So we divide the whole equation by this, and immediately we get an R here. We also get an A here, and by combining this term, by dividing it, we end up with this equation here below. And what is left to do is to replace the number of modes in the mode M from the stationary solution. If one does that, after some simple algebra, one can obtain what is x of m. Right, and x of m, what you're asked to find is this solution right here. So it depends on m, it depends on A, and it depends on kappa. Okay, so I'll move to the next. Okay, there was a question of, can you please comment on what R and XM mean physically? Well, if we look at R, so A is quite evident what A means. It's just the ratio between those two. R, if we go back, let's go back and see what R means. For R, we have atoms are pumped into the excited state with a rate R, right? This is what R is. And we have the ratio, well, we have the ratio of the pumping rate to the atoms and also the decay rate. So it's just the simple ratio of those. Okay. Then in question D, there is just a little bit of mathematics involved. And what you're asked is to assume that we can replace this sum in x of m. So I denoted by I here. We can we assume that we can replace this sum with an integral. And to discuss when this is valid for a certain relation between 1 minus a and kappa. Now, you can see that if I take, in this equation, if I take 1 over 1 minus a outside, we end up with 1 over 1 plus m squared times kappa squared divided by 1 minus a. So we expect that this sum will converge if this term is actually very small with respect to 1. And then we can replace the sum into an integral with the following, just the following manner. Here we don't use the formula that is given at the end of the problem exercise. We just simply replace the integral over m with the sum over m with an integral over dm, and here I integrate from 0 to x, and I will take later the limit of x going to infinity because we have infinitely many modes in this case. So here I have, in some sense, integrated this quantity for x modes, from 0 to x modes. We're going to use that later. So this integral to perform is also not, let's say, I would say it's trivial. It's the same thing. One needs to take 1 minus a outside, 1 divided by 1 minus a outside of the integral. In this case, one obtains this form using simply replacing this as a variable substitution equal to y. One can obtain a simpler version of this integral that is, let me write it for you. So we would have something of this sort, 1 plus y squared. This will be the integral. And then this integral is equal to the arctangent. And one replaces back the variable substitution that we did. So this integral is equal to the arctangent of kappa x divided by the square root of 1 minus a. All this divided by kappa square root of 1 minus a. And now, because we consider the limit, or we consider the case where there are infinitely many modes, one needs to take x to infinity, and the result for I is here below in green. Okay, let me use red. So here, this is the final result from the integral. And this sum, so the sum is convergent for kappa squared less than, okay, a lot less than 1 minus a, and both the sum and the integral will give the same result. Okay, so if we move further, now we have obtained the following thing. So from okay, we're asked to derive the resulting equation. Quite simply, it's just to replace the result that we obtained previously here, and we obtain our equation. I have traced it here for now, how it looks like. We're going to look into detail why this function r of a takes this form. So this is the function r is a function of a. Let's see. It's to solve this equation, but let us look at different cases now, when r is less than 1 and r is of the order of a. Now, we should not forget that we have assumed that gamma divided by big gamma kappa is very small with respect to 1, such that this term is negligible in this case for this first case, and we simply have r is equal to a, and we have a linear function. Now one can clearly see that when a is equal to 1, there is a divergence of this expression. And this is the second case here, when r is bigger than 1, meaning we look at values that are bigger than 1. A is of the order of 1. It cannot surpass 1, but it is of the order of 1. Then we can simply write this is a solution of the equation. So we just replace a that was in front by a which is around 1, and we express 1 minus a as a function of r squared, and that is the solution to the equation in this case. Okay. Now, I did not copy paste the question, but you're also asked to what is the lasing threshold? And in this case, we can see that the system changes behavior at r is equal to 1. For r that is less than 1, again, we have r which is of the order of a, because we have the linear dependence. Then we can simply replace R with A, and we find the following thing for small r, because A was of the order of 1. And here what we use is to say that R that we have found previously, which was R divided by the maximum number of excited atoms, if I'm not mistaken, divided by gamma, which will be bigger than 1. And we just find this, this is the equation that we find for the inequality that we find for the quantities that are involved. And the last, one of the last sub-questions, I have divided them in sub-questions of this question, is the laser power. By definition, we just have the sum over all energies of the optical modes, and we have taken so the sum over all energies of the optical modes will give you the total energy. And we just, by definition, the power is the derivative with respect to time, or how the energy changes with respect to time. And we can find that this is proportional, simple calculation, this is proportional to the energy times the pumping rate. So the power is the pumping rate times the energy, which makes sense. We pump energy out or in the system. And we're also going to look at the bonus question very quickly. So what you're asked for ultimately is to estimate when the laser becomes single mode 1. So instead of considering, as you remember previously, we have found we have found this integral, or this sum, in the following manner, where x now is just the number of modes. What we need to do in order to estimate when the laser becomes single mode is, instead of expanding, or instead of taking the limit where x goes to infinity, is to take for low number modes limit, which is x goes to 0. And in this case, then the following expression I will be approximately equal to this. So the number of modes divided by 1 minus A. And now simply we replace into our equation that we have previously for R that depends on A here. But now bear in mind we have this x that is the number of modes. This is the number of modes. So we need to solve for this x this time. And just by performing simple algebra on this equation, we can find the final result for x. So this will be the number of modes depending on R and A. Okay, so that was it from me. Are there any questions? Please show again. Can you please show again your explicit expressions for in 10? So can you please show again your explicit expression for number of excited maximum in 10B? Yeah, so 10B is just this. Explicit expression for, sorry, 10A. Sorry, 10A. Yes, here it is. So this is, can you please, yes, if I'm not mistaken, so this is the expression for the number of maximum. So yeah, I have not solved it here, but you see this is 1 over this expression. Then if you want to have the maximum number of excited atoms, let us see. We need to go to this equation and this is R, which was R divided by gamma divided by the number of maximum. So the number of maximum excited atoms is going to be omega divided by Q gamma. Let me see. Yes. So from this following expression, one can obtain the maximum.
If I may ask a follow-up question, should it be gamma m?
And maximum for the equality. So here it is, yeah, it is indeed gamma m.
Yeah, but then in 10C, I believe, I wrote
Sorry?
the equation for xm, and in the way you write it down with the 1 minus a, in that case, as I wrote it down, but maybe I made a mistake. No, in C, there the 1 minus a, in that a, in my case at least, it is not a gamma m but a gamma. So I had a different term, and that made it also impossible to answer question D in this case.
You mean in this one you had a different term, 1 minus a?
Yeah, I had 1 plus m squared kappa squared, and then as a factor outside of it, 1 minus a.
At the same as well.
I believe that multiple people had the same.
Let me see. So you had 1 plus this m squared kappa squared times 1 minus a.
Indeed, yeah, 1 over that entire product.
Yeah, 1 over that entire. So you had an additional term that is a times m squared kappa squared.
Yeah, and I read in chat that multiple people had the same.
And what is the in slide A for minus sign is missing? I'm just trying to understand what Mohammed is telling. Can you speak up, maybe?
Sure. So the denominator that I get is just omega over q minus nx gamma m, and it's just yeah, it's a different expression for nm, so the result will be different. That's how I guess. Yeah.
So you only get one divided by
the same expression, but just multiply the denominator by a minus. Or maybe, I don't know, maybe this is how I get it, but maybe I'm wrong.
I guess it might be possible. Let's see if we multiply by a minus.
And also considering that it asks for the maximum number of excited atoms. So it should be something smaller than omega over q, you know? So, but yeah, it's just logically doesn't make sense to me, current expression.
But then you would have a plus here or a minus.
No, that will be the same, I suppose.
Yes,
yeah. Everything will be the same, but this expression for the average number of, this
will have a minus.
Yeah. But yeah, that's just my guess.
Well, I guess if other people have obtained it that way. So by putting the minus sign here, maybe I have missed the minus sign. Then, oh, sorry. Then you obtain the right expression.
I mean, more or less, the analysis for me was the same. So,
Okay.
but just some differences in formulas. Yeah.
Okay, but do you do obtain this expression for x?
No, what I get is what just one of my colleagues said, that I get 1 over 1 minus a outside multiplied by 1 over
Plus
1 plus m squared kappa squared.
Mm-hmm.
Yeah, this is what I get.
I think the right answer is this one.
Yeah, yeah. I will look up my calculations.
So yeah, in that sense, it will be quite difficult to verify all the calculations right now to go from this step to this step. But I think the right answer is this one for x of m.
All right, more questions?
Yeah, I had another question, if I may ask. For this expression that's on this slide, for the xm, we can do a similar argument as in the exercise, that for kappa squared over 1 minus a lot smaller than 1, that the function is smooth. But the question said as a hint, prove that the series converges. And how do you prove that this series convergence? Because I used the ratio test, and it gives R as 1, so it's inconclusive in this case.
I have not proven, so I have not proven myself that this series converges, right? You are asked to, yeah, to assume that we can replace the summation over this. So you say that this is not a sufficient argument. You're saying that even if this is true, that this relationship kappa squared is less than 1 minus a, the series might still not converge.
Well, maybe it converges, but I wonder how I can see that, because the tests that we learned for this are the ratio test and the root test. I cannot apply the root test here, so I only use the ratio test, and that seems inconclusive in this case. Is there another way to see or prove this?
Not to my...
It's just purely mathematical question, right? So you're talking about expression for I, this slide. First term, investigate the convergence.
Yes, indeed.
Is it your question?
Yeah, in the question there was that this series needs to converge, and I want to know how I can see that this series converges.
In order to investigate the convergence, one has to look at large M in this case. And in this case, the terms, they scale like 1 over m squared. This sum converges. You here with me?
Yeah, I can see that if the other part is way smaller.
No.
Yeah, I find it hard to see.
I guess somehow you miss 2 questions. The question in the task is about validity of the replacement of the replacement by, of summation by integration, right? That has nothing to do with convergence in principle. All right, convergence is yeah, mathematically established. When you look at big M, you see that it scales like 1 over m squared, and that sum converges.
I think he's asking for a formal proof of why this converges.
What do you mean?
He wants to do either the ratio test or anything on the on this term to prove that.
No, sorry, one has to be reasonable. 1 over m squared converges.
Yeah, it does.
It can be computed.
Okay, but then it's still even harder to show this relation between kappa and 1 minus a.
No, I'm
with
sorry.
the
I
expression
also
for
tried
xm
to
that I
explain
found.
this during previous session when we talk about formulation. There's really nothing to think about except kind of understanding what kind of function is this. Let me repeat. In order to understand this, one can, for instance, plot it or whatever, just imagine it and compare terms which differ. What is the difference between the terms which differ by changing m by 1, just neighboring terms? Yeah. If these terms are close to each other, then the function to sum up is a smooth function of m.
Yeah.
And integration and summation just match. If it's otherwise, they don't. Then the sum is dominated by the term with m equals 0. There's nothing to think about in mathematical terms, just no fancy mathematics anymore. Just about imagining, kind of plotting or whatever, imagine in your mind what kind of function is it.
Yeah, I understand this. Only
Right.
the hint seems to suggest that you need to show that it converges, but I understand it as you explained.
That was not intended at all.
Okay. But nevertheless, I couldn't answer this question with the expression from C that I obtained. But I think it's clear now. Thank you.
All right, thank you. Also, yeah, perhaps a minor remark. So since it has been already assumed that replacement, since it has been already assumed that one can replace summation by integration, then in second line, one needs to take immediately the relation between minus a and kappa assumed here. So that immediately becomes the third line. In principle, one should not write the second line. All right. Good. Again, yeah, I'm looking at the chart. I mean, look, guys, you're physicists. You're not supposed to go to this fancy formulas. Physics is pretty practical science. It's like fixing your bank. Sometimes you read Wikipedia in order to fix your bank. That's possible. But do not read mathematical articles, please. All physics, all math which is needed for a physicist is a math in your fingers. You should not really think of convergence fancy sums. Just assume if it converges. If it does not, well, you would see that your bike would not work properly. So you have to come back and think more about this. But please, there should be no mathematical questions about this. It's just, only waste of time in this course. Let's see, it's another question from Tobias. Using this relation between A and kappa, how does it follow that A is close to 1? Or that perhaps Hristo can answer.
Well, A is just the ratio between the number of maximum, the number of maximum excited atoms with respect to the number of excited atoms. There is no problem with A being close to 1.
Okay, just to answer, but then does it mean that A equals 0 is also close to 1, or?
A equals 0 is also close to 1?
Yeah, because if I look at this expression and I take A to the left side and kappa squared to the right, then I get that A is way smaller than approximately 1, right?
I did not understand. You're talking about this expression?
Yes.
So what is it?
So if I take A to the left and kappa squared to the right, then I get A is way less than 1 minus kappa squared, which is approximately 1, right?
You mean that in this limit, the solution of A equals, you cannot obtain the limit A is almost 1 in this with this assumption.
Yeah, kind of, or at least that's also in my solutions that I think A equals 0 will yield like a convergence of the integral, right? And at least allows for the replacement.
But this is just to assume that the ratio between those two is less than 1, right?
Yeah, okay, I guess, but it confuses me.
All right, good. So if there are no other questions, let us conclude this session. Does anybody have questions about organization, about the course, about anything, questions addressed to me? Will exam be an open book exam? Right. There are two answers. Kind of short answer is yes. Long answer is as follows. Normally, it's a closed book exam, and we will not change it much in comparison with previous exams. So previous exams are pretty much the same as the coming exam. The concept of open and closed book exam is pretty much redundant nowadays, and it's pretty much redundant for any exam which is held online. Because the this distinction presumes an ability to control you about using, about opening or closing the book. All right. This ability is not present under online examinations. Moreover, it is explicitly forbidden by European law. I don't know why we could control your behavior while we kind of put you into a room and cannot control you otherwise. Ask your lawyer if you wish, but the fact that we cannot control your behavior online. It's against the privacy regulations. All right, sir. I understand why you ask this question, but this question is unfortunately redundant for online exams. Do whatever you want. From the other hand, I must give you a practical warning. Books or even electronic texts are it takes time to search them. By searching, you lose time. And eventually, I don't think you can find in the book or lecture slides things you need, at least in a finite time of exam. That's why it doesn't really matter whether you open the book or close it. Just, use the skills you are acquired in any form to make your exam. Right. So I believe I also answered the question of Calvin. And right, are there any other questions? Or whatever. If I did not put it explicitly enough, please ask more questions. Let me remember one story from the history of my examinations. It was slightly after the date when master education has been switched to English. All right, so I had to supervise an exam, and then I see in the first row a nice girl who just produced a thick book, opened it, and began to use it. I was astonished. I was really frightened by this violation of regulations. So I approached her and asked her what is going on. And the book appeared to be Dutch English vocabulary, right? Since the switch into master education has happened by that time only recently. Many students were not sure that they understand the English text of examinations. So she used English Dutch vocabulary, and that was perfectly fine. So in any case, if there are any problems, you can use English Dutch vocabulary. Fine. More questions? I don't see anybody questioning, so let me thank you for your participation in the session. It is recorded, so today, tomorrow, I will put it online. So we will see each other next time. I'm concluding this meeting. Bye.